All right, so we are going to go ahead and read through section 3, which is the ellipse. Here's our objectives. We're going to obviously have ellipses that are starting at the origin. We'll have ellipses that do not start at the origin, and then we will finish up with applied problems. Okay, if you take handwritten notes, you will want to go ahead and write this down. An ellipse is the collection of all points in a plane, the sum of whose distances from two fixed points, called the foci, is a constant. Okay. If you take a look there, we obviously have the center, we have the two foci, we have the major and minor axes. What can you see is the difference between the major and the minor? What makes it major versus minor? If you were to take a guess.
Like there's a bigger distance from the center.
That would be the guess I would go with. Okay, so let's look at ellipses with a center at the origin. So here is your theorem. I'll give you a few minutes to write that down. So it says an equation of an ellipse centered at 0, 0, and the major axes along the x-axis. An equation of the ellipse with the center 0, 0, foci at negative c, comma 0 and c, comma 0, and vertices at negative a, comma 0 and a, comma 0 is given with the equation. Okay. Assuming we will also have a theorem 2. Okay. See if we have an example. Yep. So if we're finding the equation of an ellipse, we're given the center at the origin, one focus is located at 2, comma 0, and the vertex is at 4, 0. So we want to graph the equation. So C is going to be equal to 2, and A is going to be equal to A. I'm sorry, 4 is going to be equal to A. So then we plug in what we know. And we solve for B. Okay. Here they kind of hand drew. I guess they technically cheated and used a program. Does that look like something you guys are going to be able to handle? Yeah, I think so too. Okay, so here it says using a graphing utility. First solve for y. And then here you see we're going to have a square root. So what do you think is going to happen when you plug it into either Desmos or your graphing calculator? What do you think you're going to have to do? So you can see the entire function.
You have to make two separate equations, one with negative and the other positive.
Exactly. Okay. So if you take a look at the next slide, that's what they show you that they do. Take a look at what they're telling you down there. They're saying all conic section graphs are created using zoom square to avoid distorting the graph. So if you try to use your regular calculator instead of Desmos, you're going to want to use zoom square. Okay. And you can see that, yes, they had to use two different equations in order to get the full ellipse to show up. Okay. Here we have a third example. And then I think we're going to go on to the next theorem. So here we're given a squared as 25 and b squared as 16. So of course, to get a and b out, we would take the square roots, but we'll get c squared instead. Right? Plug everything in. Here they give you the hand-drawn as well as the graphing utility. Okay. Go ahead and write down theorem 2 if you're taking handwritten notes. This is going to be pretty similar to theorem 1, except notice that the major axis is now lying on the y-axis. Okay. Let's look at another example. If we're given 9x squared plus y squared equal to 9, we want to make sure that the x squared term is a 1. So we're going to divide everything out by 9. Okay. If you do that, that's going to verify to you that you have the major axis along the y-axis because your denominator is larger with the y unit. Okay. All right. Here you can see that they graphed by hand and also utilizing a graphing tool. I would prefer for your exams that you hand draw your diagrams. If you choose to use Desmos, I would prefer if you do a screenshot or a snippet or something so I can see what you're actually doing. All right. Okay, if we have an equation of an ellipse having one focus at 0, 3 and a vertices at 0, -4 and 0, 4, and we want to graph the equation. Okay, so we get C is equal to 3 and A is equal to 4. That's if we follow along with the definitions. So if we have A and C, we can then get B, and we can plug everything into the function. And then you can see that they went ahead and drew out. Okay. All right, that's basically how easy it is for ellipses at the center or the origin. I would write this table down. I can guarantee you'll have questions on it from Pearson. Recently, they've liked to ask a whole bunch of definition-based questions. Okay. I'm not going to go through and read the table. It's there if you need it, along with some really nice diagrams. So I would take the time to write it out or take a picture of it. Or if you need to come back and watch the video, you can do that. If you have the textbook, it's in the textbook as well. The book is giving the hint that it would be better to use the table than to try to memorize transformations. I'm assuming it's just easier to plug things in versus trying to figure it out mentally. All right, let's look at an example. Let's find an equation of an ellipse at the center with a center at -1, 2, one focus at -3, 2, and the vertex at -5, 2. And then graph the equation. So let's break down what we have. Our center is HK, and it's given as -1, 2. So we have H at -1, and we have K at 2. Okay. So if we plot the center, the focus, and the vertex, we're going to realize that everything's lying on the line y equal to 2. So then again, we have a major axis along the y-axis, basically. It's parallel to it. Well, I guess parallel to the x-axis. All right. The distance from the center to the focus is c equal to 2, and the distance from the center to the vertex has a equal to 4. So then again, we plug in to get our b squared. Okay. And then it's just as easy as following the formula. And again, they're getting this equation from where? Where are they pulling that from?
From the center. I mean, the point in the center.
Right. So that's what they're using it from, but they get the overall equation just back up here from the table, right? So that table is going to be pretty important. Okay, so once you plug everything in, you end up finding your vertices or verifying your vertices. Okay. So you have to use that to find your foci 1 and your foci 2, your two foci. So they found the square root of b squared, or they found b, and then they plugged it in to find the 2 points. And these will be the points that sit above and below the center. So a little bit more work goes into it when the center is not 0, 0. Here is your hand-drawn graph. All right, let's look at another example. We want to use a graphing utility to graph the ellipse that's given. So the first thing you want to do is solve for y. What do you think your next step is going to be? You've gotten to the point where y minus 2 quantity squared is equal to the right-hand side. So what should we do?
We see the square root of both sides.
Mm-hmm. And then you're going to bring over the 2. So remember, you need to split your y into y sub 1 and y sub 2, or you're not going to get the full graph in a graphing calculator. I assume it will be the same for Desmos, and you will have to do a y sub 1 and a y sub 2. Now, take a note that on the graphing utility, at least on this one, it's not a complete ellipse. So you're going to have to know that as the mathematician and make sure that when you draw yours, that you're connecting it. Okay. Let's look at what I believe will be our last example. We want to analyze the equation of an ellipse. Okay. Somebody walk me through what they're doing. What did they have to go through and do? Okay, take a look. They went through and they completed the square both in terms of x and in terms of y. If I were to take a guess as to where students would make a mistake, it would be on remembering to add on the right-hand side each piece. Okay. Then you just pull out what you need to pull out. You have your a squared and your b squared, so you find c squared. And then you can figure out which part of the table you want to look at. And that's going to help you find your vertices and your foci. Once you have all that, you can just go ahead and either draw it by hand or use the graphing tool. Any questions on those two objectives? Okay. All right, solving applied problems involving ellipses. All right, so here we're going to learn a little bit about a whispering gallery. The Whispering Gallery in the Museum of Science and Industry in Chicago is 47.3 feet long. The distance from the center of the room to the foci is 20.3 feet. We need to find an equation that describes the shape of the room. How high is the room at its center? Obviously, that was taken from the website. So we're going to set up for an ellipse. Okay. Since the length of the room is 47.3 feet and the distance from the center to each vertex, we need to divide that by 2, so we get 23.65 feet. So A is equal to 23.65 feet. C was given to us as 20.3 feet. So there's half of your ellipse already. Okay. What does that tell you about the height from the center? Can you get that already? What's the height from the center?
12.1.
12.1 feet. Okay. So they must have prematurely drawn their diagram, because you can see that they went through and they figured out their 12.1 using the information that was given. So I guess it just kind of depends. If they give you this, if Pearson gives you something like this, you can just go based off of your knowledge of a graph. If they don't give you that, then you'll have to go through and find it. Does that make sense? Okay. Any questions on ellipses before we switch over to the hyperbola? All right. We will have to have a third day for chapter 11. And I haven't decided yet if we're going to go over section 5 or not. It's not traditionally covered. I am going to take a look at it over the weekend and decide if we're going to cover it on Monday or not. But hopefully, we will only need to do one more day of notes after today. And then we'll figure out what we're going to do next. Okay, so objectives for the hyperbola. We're going to look at a hyperbola with a center at the origin. We're going to find the asymptotes of a hyperbola. We're going to analyze hyperbolas with the center other than the center at the origin, and then look at applied. Here's your definition if you take handwritten notes. So a hyperbola is the collection of all points in a plane, the difference of whose distances from two fixed points called the foci is a constant. So it's kind of like taking the ellipse and folding it outwards instead of making them come together. Okay. All right, so let's take a look at hyperbolas with the center at the origin. All right. So here's our first theorem. An equation of the hyperbola with the center at 0, 0. So notice that the foci and the vertices are very similar to what we had with an ellipse. What do you notice is different between the ellipse and the hyperbola?
It has a minus sign instead of an addition sign.
There we go. And that makes sense, right? Because if you took an ellipse and you folded it the other way out instead of in, then we would be subtracting instead of adding. Okay? Really the only difference between the two. So do you think that is going to mean that we can have it being parallel to either the x or the y axis? Just like we did with the ellipse? What do you guys think?
I think it, yeah, it could be parallel as well.
Yes, I agree with you. Okay. Let's take a look. All right, so here we're looking at an equation of a hyperbola. The hyperbola has a center at 0, 0. So we're going to plot the center, the focus, and the vertex. The focus for one focus was given as 3, 0, and for the vertex, it was given as -2, 0. So we're looking at a C equal to 3 and an A equal to 2. Okay. So if we plug in, we get the following equation. X squared over 4 minus y squared over 5. Okay. So then to graph the hyperbola, we want to locate and plot some other points. Okay. So we're going to look at points that are above and below the foci. So we're going to use both plus and minus 3. Okay. All right. So the points below the foci are plus or minus 3, and we get 5 over 2 as the y, or we get -5 over 2 as the y. And then you can take a look at the hand-drawn hyperbola. Okay. If we were going to use a graphing utility like Desmos or your graphing calculator, which again, I still don't know if I recommend that. I would probably just use Desmos, but you guys can let me know if you end up using your calculators. My calculator is not, I still need to kind of prep and figure it out. Need to watch a lot of YouTube videos for it. So what are we going to have to do? Our functions include what? Can we graph the function of a hyperbola by itself in one of those graphing tools?
No, we need to do the same thing as we did for the other functions.
Right, because we not only have this time one square root, but we actually have 2 square roots in our function. So luckily we can keep them kind of the same signs if we put the signs out front. So yes, we very much need to do that. And again, we're going to use the square zoom, or else you will get a distorted graph. There you can see an example of a graphing utility of a hyperbola. Honestly, I would do it by hand. I know it's old school, but I definitely did not learn this stuff drawing it into a calculator. When I was doing this kind of stuff, I did it by hand. Is that the one we just did? Yeah. Okay, so here's our next example. We're given x squared over 25, which means we have an a squared equal to 25, and we have minus y squared over 9, so a b squared of 9. We're going to solve and find c. So c squared is equal to 34. You can take a look at what your vertices and your foci are going to be down at in the last sentence there. Okay. So we now have to locate the points above and below the foci. All right, so they're going to use plus or minus the square root of 34 because we want to know what's above and below it. So we end up getting out a 9/5 and a negative 9/5. And again, we have to use two functions in order to graph. Here you can see they chose to graph it by hand. Again, that would be my recommendation. I might even give bonus points if you graph your items from chapter 11 by hand. All right, here you can see they did go through and put it into a graphing calculator. They, of course, had to split the functions. I will give you credit if you get into the habit of doing a function 1 and a function 2, or a y sub 1 and a y sub 2. If it asks on the exam for just the equation and you give me 2 of them, I will give you credit. But obviously the preference will be for you to give one function. All right. Let's look at the center 0, 0. But this time our transverse axis is going to be the y-axis, meaning that's where the hyperbola is going to go through instead of through the x-axis. This is your theorem too. So I would pay attention to it if you like writing your stuff down. Okay. Let's take a look at an example. Here they went through and divided so they can verify what their transverse axis is going to be. They found their a squared, their b squared. They used that to find their c squared. They found their foci and their vertices. Okay. A lot of this is plug and chug, really. It's kind of taking you back all the way to algebra 1, where you just basically were learning family functions. What do you notice is different this time when you have to locate points? Instead of them being above and below the foci, what are they? Where are the points going to be found at? Are they going to be above and below? Where are they going to be? They're going to be left and right. Okay? You got to pay attention to what direction you're in. Okay? So here's your hand-drawn example. Right? Here is your graph utility example. Again, they had to split their function into y sub 1 and y sub 2. I do apologize for not being able to make these presentations any more lively than basically walking through them and answering any of your questions. All right. If we were to find an example, find an equation where one vertex is 0, 2, and one foci, or the foci are 0, -3, and 0, 3, and we want to graph the equation. What does the foci help us find? Foci helps us find what? Anybody? It helps us find the C. Okay. The vertex helps us find the A. So together we can use that to find the B. And then once you have A squared and B squared, you can find the equation. Okay. The foci also helps us find the points to the left and the right of the foci. All right. So that is the final answer there, but then they also chose to give you the graph of it. Okay. All right, now we're going to talk about finding asymptotes. Here is your theorem 3. Write it down if you take notes. Okay. So basically the asymptotes are going to be found at y equal to b over ax and y equal to negative b over ax. If we were to prove that, what do you think we would do? If I didn't believe this slide, how could you prove to me that that's correct?
You can plug the coordinate that you get into the actual equation.
Yeah, I mean, you could try to do that. I'm not really sure if they show you. What was the difference between here and here? Ah, they've flip-flopped the positioning of the A and the B. Still basically the same statement. So if you had to prove this, you can kind of take, you can take the approach of if you start from this function, right? Okay. If we start from here, then we need to solve for y. Okay. Well, we're going to add x squared over b squared to both sides. Okay. I guess technically we're solving for this one and proving it. Apologies. So we're going to, So then that changes these. Stop it. Okay. And then if we take and multiply b squared to both sides, okay. Makes this a negative. Makes this a negative. What do you think? What do you think we can use now? What do you think we can do? Okay. I will help you. So if we rearrange, we know that x cannot be equal to 0. So we end up getting y squared equal to b squared a squared over, or x squared over x squared over a squared 1 minus a squared over x squared. Okay. So then y is going to equal plus or minus bx over a square root of 1 minus a squared over x squared. Now, what do you think the last step is to do? We have to basically get rid of this part. So now we're going to bring in some calculus. So if you take the limit of this function, the limit as x approaches plus or minus infinity, then this section here becomes a 0, which is going to leave you with y equals plus or minus bx over a. That would be your proof, okay? And I know that took a little bit of time, but sometimes I like to show you I know how to do math. All right. Any questions on that? I don't think you'll have to do anything like that, but I did want to show the proof of that for you. Okay. So let's analyze the equation of a hyperbola. If we're given y squared over 4 minus x squared equal to 1, so we're going to have a hyperbola at the center, and it's going to traverse along the y-axis. We're given a squared equals to 4 and b squared equals 1, so we get c squared equals 5. You can find your foci and your vertices. We also know that a equals 2 and b equals 1, so you can find the asymptotes. They're going to be at y equals 2x and y equals negative 2x. So here's your hand drawing. Okay. Same thing with this, except now we're going to be going the opposite direction. If I go a little bit too fast for you now, you can watch the video later. Or you can check out the PowerPoint on Canvas. Okay. So objective 3, we are looking at hyperbolas with a center of HK instead of at 0, 0. I recommend writing down the table, whether you do it now or when you watch the video. It is recommended to have the table available to you while you work through these problems. You can see they have a nice hand-drawn diagram for you for each set. Okay. Not going to massively go through these examples because I feel like they really are just plugging in as if you were going way back to learning your family functions. Okay. Here's an example. Here's the hand drawing of that one. Okay. Notice for this one, they had to complete the square for both x and y before they could go through and find the equation of the hyperbola. So if you're told that an equation is a hyperbola, or if it looks like it could be, and it just doesn't look like it's in the right form, you might have to do that. So please, on the test, don't tell me that the hyperbola does not exist or something. Try to remember these examples. Okay. So here's your hand-drawn equation. Obviously, if you put this in the graphing calculator, you could not label it like this. You'd have to split it up. And here they show you that. So it's the same function, but when you do the split, it looks very different than the function they gave you originally. And we'll do our applied. Lightning strikes. Suppose that two people standing a mile apart both see a flash of lightning. After a period of time, the person standing at point A hears thunder. 1 second later, the person standing at point B hears thunder. If the person at B is due west of the person at A, and the lightning strike is known to occur due north of the person standing at A, where did the lightning strike occur? That sounds like something that we would find on the SAT. Okay. So the ordered pair XY represents the location of the lightning strike. We know that the sound travels at 1,100 feet per second. So the person at point A is 1,100 feet closer to the lightning strike than the person at point B. Okay. Since the difference of the distance from XY to B and the distance from XY to A is a constant at 1100, the point XY lies on a hyperbola whose foci are at A and B. Okay. Keep in mind that they switched it from 1 mile to feet because feet are what we were given for the 1100. And I would definitely give you bonus points for drawing the diagram and not trying to figure it out just in your head. An equation of the hyperbola is given as x squared over a squared minus y squared over b squared equal to 1, where a is equal to 2. You find a by taking 2a equal to 1100, so a equals 550. C is found by taking 2c equal to the total number of feet in 1 mile. So C is equal to 2,640. So obviously they figured these numbers out prior to the drawing. All right, so now they found their equation. Since the lightning strike occurred due north of the individual at point A, we let x equal to 2,640 and solve for the resulting equation. So the lightning strike occurred at 12,122 feet north of the person standing at point A.